Hello everybody, welcome to my community problem number 4, and today we're going to look at a function, and this function is determining the average cost of producing a chemical in hundreds of dollars, and this is based upon how many tons of a substance are produced. So it's the cost of hundreds of dollars per ton. So um, depending on how many tons are made, that will determine how much it costs per ton to make it. So first we're asked to um, find the answer for 1 ton produced and 15 tons produced. If we, one second here. So here's our function, and if we plug 1 into that function, um, do a little bit of math here and pretty simple stuff. 1 plus 1 is 2. 2 squared is 4. 50 divided by 4 is 12.5 plus 4 is 16.5. So uh, the cost to produce, the cost to per ton to produce 1 ton is 16.5 $100. And for the cost per ton to produce 15 tons, we're going to plug 15 in here. We're going to get 16. 16 squared is 256. And we could write that in a fraction for adding the 4 to that. We're going to get 4 and 25 128ths, or this decimal number here, 4.19, so on and so forth. So the cost to produce 15 tons, or the cost per ton to produce 15 tons, is $400 $400 and change. Um, Now, if the thing to notice here is that it's less. It's not a total cost. The total cost to produce 15 tons, um, in this case, let's just multiply this. Oops, 15 times 4.19. No, that's in hundreds. It's over 6,000, whereas in the other to 1 ton it's only let's see here, 16.5 times 100. It's only 1,600. Okay, so it costs more to produce more tons, but per ton it is much less. It's cheaper per ton the more that they make, which makes sense if you've ever bought in bulk or sold things in bulk or even produced things in bulk. You save money that way. So that makes sense. Now on to the second part. We want to find the inverse of this function. So going down here. So how do we find inverses? So an inverse function is basically you're taking a function. With a function, you have an input and an output. The inverse of that function is switching the inputs with the outputs. So, and also on a graph, it's just like mirror. It's like a mirror of that. And basically, what we're saying in the original function is we're saying how much does it cost per ton to produce this chemical, um, based upon how many tons we make. So the input is the tons, the output is the cost for the original one. In this one, we're saying, okay, we have a cost, how many tons, or the output would be the tons, and the input would be the cost. So the way that we figure this out is by switching the x's and the y's. That's what I'm getting at here. So f of x, that's basically a y. That's an input. In this case, it's c, but I'm just going to write it below as y for simplicity's sake. And in this first part, I got stuck, so I did it another way. But I'm just going to go over it so that way somebody can give me some hints as to how I messed up, or if I was doing it wrong the whole way, or if I could have done something else to finish going along this line of algebra here. So basically, again, f of x is y. So I'm going to change that into an x. And on the right-hand side where I have x, I'm going to change that into a y. Okay. So the first thing I did was I FOILed out this squared expression here, and I got a y squared plus a some y in the denominator. I subtracted 4 from both sides. I got x minus 4 over here. I turned that into a fraction. And then I cross multiplied. Sorry, no I didn't. I took the reciprocal. And then I multiplied by 50 on each side to get rid of the denominator. What we're trying to do is isolate our y values so we can say y equals something. But this is where I got stuck because I wasn't sure how to get rid of the y squared. I mean, obviously we could take square root, but then I just got a little confused here. Maybe it's something simple. Please help me out there. So what I did was I just backtracked. I went back to the beginning and I just did it a different way. So looking back at our function, I started by subtracting the 4 first. So I got an x minus 4 on the left. I turned that into a fraction over 1. I still left this in its squared format here. And then I cross multiplied. So I got a 50 on the left, and I got these two things multiplied on the right. X minus 4 times y plus 1 squared. Then I divided by the x minus 4, so I got the x minus 4 back over here. 50 over x minus 4. And then I took a square root of both sides. So what I got was y plus 1 is equal to the square root of that fraction. Subtracted 1 from both sides, and then I got my final inverse function, which is inverse of f of x is equal to the square root of 50 over x minus 4, all of that minus 1. If I could have simplified this more, please let me know. I am not sure if I could or should, so that's where I stopped. But this appears to work, so I think we're good to go. And we were asked about the domain. What is the domain of the function? Oops. What is the domain? So what I came up with, the first thing I notice is we're dividing, right? So we don't want there to be a 0 here. So we can't have a 4 there. Can't divide by 4. So also we have a square root, and we know if we want a number that's not imaginary, we don't want a negative number here. So that tells me that x needs to be greater than 4. If it's 4 or less, we're going to be in trouble. Also, we have this minus 1 here. Don't forget about that. And I stuck this into the graph, Desmos graph, just to double check my answer. And as you can see from the graph, for our x values, you see that there's an asymptote. You can't get to 4. If you try to get to 4, you're going to have a bad time. You're going to get undefined. Nobody wants to be undefined. Don't let your life be undefined by mathematics. So it also, I triple checked it with a chart here. I put 4.00001, and we get a result. But 4 itself is undefined. Anything less than 4, undefined. I mean, that's easy to tell by the graph. Everything above 4 going this way has a number, get an output. So we should be good with our domain there. X is greater than 4. And next we want to find and interpret an input of 5. So that's, again, we're flipping it. So we're saying it, in the first one, X is the tons produced. So in this one, X should be our cost. Hope I'm saying that right, but anyway, well, let's look at our solution here. So plugging f into the function, down here, or sorry, 5 into the function, we get 1 on the bottom. So square root of 50 is 7.07 something, minus 1 is 6.071. Checking that on our calculator or graph, you can see 5 is 6.071. And again, these are inverse functions, so we can see this on the graph. Oops, where'd it go? Oh, there it is. Okay, so the blue one is our original function. And if we do this, y equals x, we can see that there's symmetry on both lines, so they, they look exactly the same on the, either side, left or right, or top or bottom, however you want to view that diagonal line. Maybe tilt your head to the side a little bit, or this way, whichever works for you. But those are mirror images of each other, and also, if we were to plug this number 6.071 into the first function, which I called p here, we see that we get 5 basically. It's a rounded number, but we see that works. It goes forwards and backwards. If you plug the output of the inverse function, if you take the output of the inverse function and make that the input of the original function, you will get that 5 again. Okay, your output will be your input. Hope that makes sense. Hope I said that clearly. But yeah, that seems to work. We're good to go. Let's go to part 2. And part 2, we have this function here, crazy looking thing. It's called h of x, and it's got some algebra in there with a sine of a square root. And what we want to do here is want to decompose or break this thing apart into 2 smaller functions. Now, why do we do this? Basically, we're just trying to show how we may be trying to show how things are related. So I'll just use the example that came from the textbook, and also Professor Malley went over. It was this one. This was actually, we started with the 2 smaller ones and made a bigger one. But we had, in the broad example, we were saying, hey, what is this person's, some patient's heart rate? What is that over time? That was the bigger function. But in reality, what we started with was 2 smaller functions. And the 2 smaller functions were actually saying, hey, that we have this person's heart rate based upon the quantity of a drug that's in their body. That's how we're getting their heart rate. And we also were saying, hey, we can figure out how much of this drug is in their body based upon how many hours have passed since it was given to them. Okay. So again, the bigger function was relating those 2 things together. And what it was saying was, well, hey, since I know those 2 things, what is the person's heart rate based upon a certain amount of time? Okay. I hope that makes sense. And in this example, we're given the whole a whole bigger function and breaking it into 2 smaller things. So what does this find? We don't know. It doesn't matter. What are the 2 things measuring or calculating? Could be anything. Could be nothing. But let's make it work. So going into here, we can see that there's our function there. And the way that we want to decompose this is such that we can still find h of x by first finding g of x and plugging that into f of x. So h of x is equal to f of g of x. Okay. So for g of x, I selected this little portion here, 2 of x minus 1. I said, hey, let's find this first. Okay. Therefore, since we did that, f of x must be um, 3 plus sine of square root of x, all of that squared. So basically just everything that's left over um, must be f of x. And in order to find f of x, we need to find g of x. So if I say f of g of x, that another way to say this could be, instead of the x, we put the g of x there. Okay. Or more specifically, we put the 2 of x minus 1 in there, which is the same thing, essentially, as the original h of x. So theoretically, that should work. I did by hand, the first most simple thing, plugging 1 into it, and you get 1 for g. But then if you plug 1 into f, you get 14.75, so on. Also, if you plug in 1 into h, you get that same number. Okay, I'll show you that in a second on Desmos. Now, for the second second set or example of a way that we could break this up, it's not much different. I just included the radical. So g of x is the radical of 2x minus 1. And it makes sense. Normally when we see a sine function or sine of something, there's a parentheses there. Even in Desmos, it'll get upset, not know what to do if you don't put parentheses there. So my sine x or sine parentheses, that is my g of x. For f of x, therefore, we must have 3 plus sine of x, all of that squared. And again, plugging 1 into f, you get that same thing that we did up here. So that shows that this does the same thing as these two smaller ones do the same thing as these two smaller ones up here. And I just, wanted to really double check things, so I also plugged this into Desmos. And let me just get rid of this guy here. Don't need that. So there's our, in the first set of functions where g of x doesn't have the radical. There's the f of x. And here is h, which is f of g of x. So as you can see, it looks a little different, right? And you can really see why when you look at the table of values. If you look at how these things are related and you kind of play around with it, that's where things really start to make sense. And really what you can do, I did the 1, although in this particular example, 1 doesn't really help us because of the square root. You kind of have to use a bigger number to really look at stuff. But h of 1 is that same number there, 14.75. This here, which is basically saying the same thing as f of x, you get the same number. But the interesting point here, if you plug 4 into the g function, you'll get 7. Okay. Now because this is fed into f, f is whatever the output of g is. Or sorry, your input for f is the output for g. So if I put 7 into f, then I get 12.08, so on and so forth. Now, here's how we know that it works, is because h of x is equal to f of g of x. What I'm saying is, okay, whatever my output is for g, well, I have an input. Okay, but first, whatever I get with g, let's plug that into f. So output of g is the input to f, will then be my output for h. So if I put 4 here, like I did for G, I get the same thing as if I put 7 into F. Now, I don't know if I'm saying this the best way. I really had to work through this and like look at different examples and look at the table of values. Um, I still need to learn how to use table of values on Desmos. I'm sure, oh, there it is, table. I was doing it earlier, but I'm not going to mess with it right now. I'll leave you up to that if you haven't done it yourself. Oh, there it is right there. Oh yeah, because I had this table up here. Sorry for my confusion. I'm still getting used to this. But basically, you can make a table. You can make a table of these functions, put them all 3 of them together, and look at a set of inputs, maybe like 0 to 10 or 1 to 10, um, and look at all those inputs and outputs, and you can see where your inner functions um, output, okay, um, when you get an inner functions output and you look at the input for the next most outer function, uh, that should match the the overall um, output if the inputs are the same for the innermost. Okay. So again, I don't know if I'm saying this the best way, but just go ahead and look at the table. I'm not going to do it right now, but that should help sort of make things click for you. But yeah, that's going to do it for now. Hope you survived the video. Please, somebody, give me hint here where I messed up here, um, or how I could do that better. Or if I did something wrong, please let me know. But anyway, have a good one. See you around, and take care.